Welcome and greetings to all from the OMNI-X USA team. We are excited you could join us for the inaugural launch of the OMNI-X educational webinar series, designed to empower our customers when making tooling decisions. I am your host, Michael Stelbaski. Today's topic, Mandrel Overview, will be presented by Jack Downer and Scott Mitchell. The presentation will take approximately 25 minutes, followed by 15 minutes set aside to address your questions. We encourage you to submit your questions at any time during the webinar through the chat box function. And all questions will be answered after the presentation by the OMNI-X team. Today's agenda will cover 7 primary points, starting with when to use a mandrel, Mandrel styles, thin wall and ultra thin wall ball configurations, inserted nose mandrels benefits, determining clearance, choosing compatible materials, and lastly, reviewing the pros and cons of alternatives. I will now turn the mic over to our first presenter, Jack Downer.
Thank you, Michael, and welcome everyone. We will start this webinar with some Mandrel basics. The purpose of the mandrel is to provide internal support of the formed tube. This primarily occurs in the outside radius of the bend to keep it from collapsing, and from the inside radius of the bend to keep it from wrinkling. The difficulty of bend determines the complexity of the mandrel required for the job. The need for a mandrel is based on 3 main things: application type, finish quality of your end product, and all factor of your application. We'll now look at a basic mandrel and wiper die selection chart. And this chart is a tool that provides the direction for the kind of mandrel needed when high quality bends are desired. We'll cover this chart in some detail today. There are 3 parameters that drive the use of this chart: tube OD, wall thickness, and bend radius. There are 2 formulas shown here on the chart on the left. One is for the D of bend, and the other is for the wall factor. The D of bend that people are most commonly aware of is where you take the bend radius and you divide it by the tube OD. The wall factor is determined by taking the tube OD and dividing the wall thickness into it. Once you have those 2 parameters, the wall factor runs on this side of the chart and your D of bend goes across the top. As an example, if we had a wall factor of 25 and a D of bend of 2, we'd come in here and we would see that we need 1 ball with a mandrel, and it's shown M1W. What you'll find is that as your radius gets bigger or your D of bend increases, you'll see some spots out here that actually are blank. These indicate that you don't need a mandrel at all. But as the radius gets tighter or the wall factor increases a little bit, you'll start to see a P show up, and that indicates a plug mandrel. Then you'll see where it's an M1, which is a mandrel, but there's no W, so you don't need a wiper. As we get more complex and tighter, you'll see that you need additional balls on the standard pitch mandrel, and then we start to get into the thin wall mandrels shown as the TW, and is more complex, the ultra thin wall mandrels. The overview of this chart shows that the larger the tube OD and the smaller the bend radius of your tube, the more difficult the bend. Next, we'll talk about mandrel styles. The 4 configurations shown in this view provide the most common mandrel styles, from simple in the plug to the ultra thin wall, more complex. We'll go over them in more detail in the next slides. If an analogy or a picture helps, the mandrel and the tube are basically in a wrestling match with each other. When the tube is stronger, you need the strongest mandrel link to resist breakage. When the tube is thin and the material is more likely to collapse when being stretched. As the outside radius is being stretched, it becomes weaker and needs more support points, as you'll see here, versus on the thin wall and ultra thin wall mandrels. And this is when the links go smaller and the ball configuration is changed to accomplish more support. Next, we'll talk about plug mandrels. The plug mandrel styles are basically three different ones, and we have two shown here. The standard plug is the simplest style, providing a forming surface at the nose of the shank. And since the mandrel stays stationary at tangent, which is this point right here, and your clamp and bend head rotate around and this stays stationary, the forming always stays at tangent. For more complex plug mandrel applications, you need some additional support beyond the tangent area where the forming occurs. This support can be provided in either a universal radius or a specific radius to your application. The full radius plug mandrel has additional material out here in the nose, kind of in the shape of a bullet. The formed end plug extends further into the bend. We still have the tangent point here where the forming is occurring, but now we have material out into the bend that is designed specific to your bend application radius. One key note is that with this style mandrel, you need to make sure that it's locked down tight so that it does not rotate on you. Next, we'll talk about the standard pitch mandrel. Once the application needs more support than a plug mandrel can provide, a ball mandrel is the next step. The balls not only provide support on the outside radius of the bend, but it also helps to keep the inside radius smooth and the tube round after bending. The number of balls on the mandrel depends on the level of difficulty of bend and personal preference. However, you need to be careful not to have too many balls on the mandrel, as each additional ball adds more drag that your clamps must be able to compensate for. Too many balls can create excess load and cause clamps to slip and wrinkles or tears can result in your tube. The balls are sized about 5 thousandths smaller than the shank to keep the load on the shank and not on the balls during the mandrel extraction process. The standard pitch mandrel is the strongest configuration of the ball link style mandrels, as it uses the largest link possible for the application. If the support provided by this style of mandrel results in the quality of bend that meets your needs, it's the best mandrel for your application. We'll now use this animation to show the difference between the standard pitch mandrel, which is shown here. And once I click the screen, you'll see first the closed pitch, then the ultra closed pitch. So here is the closed pitch. And now here is the ultra closed pitch, and you can see where you have additional pressure points or load points to help support the tube, and the gap between the balls gets smaller. Thinner wall tube requires more support during bending to keep the thinner material from flowing into the gap between the balls on the OSR of the bend. The way to offset the material sagging issue is by bringing the touch points between the balls closer together using a smaller link size and increasing the number of balls and changing the configuration of the balls so that nest to minimize the wrinkling on the ISR. To provide the best support, these mandrels styles, they use two different types of balls. The ball next to the shank is called the end ball. The balls added on after the end ball are called center balls. The thin wall mandrel, sometimes called the closed pitch, has a link size that's one size smaller than a standard pitch mandrel, and the ultra thin wall mandrel, sometimes called an ultra closed pitch, has a link two sizes smaller than the standard pitch mandrel. For example, if the standard pitch mandrel has a number 9 link, the thin wall will have a number 8, and the ultra thin wall will have a number 7. The next slides will offer some detail about the components and ordering option of the balls we have been discussing. All the mandrels can be taken apart and reassembled by the user. Each of the components can be purchased separately. In the case of the ball mandrel, customers, they initially purchase a complete assembly. Then when the components wear or need replaced, they buy individual balls and links to replace the worn components, and you can purchase what is called a standby assembly that is shown up here in the upper right corner. And that's basically the entire mandrel without the shank. There are 3 different types of links, and they're shown here. We have the shank link, which is a barrel shape and goes into the shank to secure, and is secured with a cap head screw, which is shown here on the standby assembly. The end and the center link, which is used for adding additional balls to a 1-ball mandrel. The key to note when replacing components is to measure your nose of the shank in the forming area and make sure that it's still bigger than the new balls you are putting on. If the balls are bigger than the shank forming area and the shank may not be doing the job that you need, when you retract the mandrel, the load will then be going on the balls, increasing the chance that the ball string will separate from the shank and be left in the tube. As previously noted, with thin wall and ultra thin wall mandrels, there are now 2 different ball configurations used to provide the best support. In the thin wall and ultra thin wall mandrels, the shape of the end ball is made different as it does not move as much as the other balls, and it sees higher pressures being near the forming area and does not need to nest with the shank. The other ball configuration, called the center ball, are added on after the end ball. The center balls are designed to move more during the bending process and nest, as we show here, on the ISR to provide the maximum resistance to the tube trying to wrinkle during the bending process. Next, we'll talk about inserted nose mandrels. The nose of the mandrel shank is where the forming and highest pressure occurs during the bending process. As a result, this area needs to be monitored to ensure you have enough support and that the excess wear does not occur, allowing too much clearance, resulting in too much reduction of your bend quality. You can certainly replace the shank when this occurs. However, this component is the most expensive part of the mandrel. If you have high volume applications or need more versatility for different materials of the same OD and wall thickness, using an inserted nose mandrel can be an excellent and cost-effective solution. The cost of the nose is about the same as the cost of a ball. This option is available for all mandrels as small as 1.25 OD. The inserted nose mandrels also provide the option of buying a complete assembly, individual components, or a standby assembly that includes the nose, and all you have to do is remove the cap head screw from inside the shank body, remove your old standby assembly, and install a new one. Now we'll talk about clearance. Too much, too little, or just right. Clearance is the space between the ID of the tube and the finished OD of your shank and balls. The amount of clearance determines the amount of opportunity there is for the deformation in your finished product, OSR flatness, ISR suck-in, and tube out of roundness. There are 3 different clearance standards: aerospace, automotive, and shipyard. Aerospace is considered the tightest tolerance in the 3 to 7 thousandths range. Automotive provides a bit more clearance in the 10 to 15 thousandths range, and shipyard, which we usually see heavy wall, pipe and tube, has clearances typically in the range of 25 thousandths and up. Too much clearance allows for more flattening in the OSR and waves or wrinkles that can develop on the ISR. Too little clearance can create drag, putting more load on the grips and potentially providing slippage that can also, providing slippage. Too little clearance can also squeeze out your lubrication, creating more drag. The worst case, the variation of your tube material may not even allow you to load the tube over your mandrel if your mandrel is not sized properly to the tube. A keynote about the material specification: the range of variation of the dimensions of the tube allowed by the spec can exceed the automotive and aerospace bending clearances we discussed above by 2 to 3-fold. Understanding the sizing of your material or having a mandrel size to your specific material can save you a lot of unexpected issues, scrap, and cost from one lot of material to the next. When you're using material with weld seams, it adds another layer of issue to discuss outside this presentation. Material compatibility. Typically, mandrel recommendations are intended to avoid galling between similar materials. Soft tubes need hard materials, such as steel, copper, and aluminum, get the best life using a tool steel chrome mandrel. And hard tubes need softer materials, i.e. stainless steel, titanium, and Inconel go with aluminum bronze mandrels. The 2 forms of bronze shown here are AB18, which is the industry standard, and ABX, which is a harder, more durable option offered by OMNI-X for about 25% more cost and provides 2 times the life. The next area of discussions are alternative materials, alternative tooling configurations that may or may not require a mandrel. And to handle these areas, I will pass the baton to Scott Mitchell.
Thank you, Jack. Sometimes applications that are higher volume or have very specific quality standards will benefit from different materials. For typical high volume automotive applications, industrial coatings can offer longer life for mandrel components. Since tube bending is a slow but high pressure process, typical coatings from other industrial processes don't always work well. Coated mandrels also require a substrate tool steel that is specific to the coating. Thermal diffusion, TD coating, is the hardest and most durable of the coatings available, although it isn't a true coating in the sense that it is diffusing carbon into the face of the part to create a super hard carbide layer. This has no bond strength issues like other traditional coatings can have. Chemical or physical vapor deposition, CVD or PVD coating, is a coating that is applied in a lower temperature environment but can offer some increased lubricity that TD coating normally doesn't have. Typical CVD and PVD coatings you may be familiar with are TIC, TICKN, and DLC. There is occasionally a bond strength issue since this is just layered on the outside of the part, but under normal use it isn't a major concern. Duplex coating often combines 2 different processes, normally nitriding and some kind of applied coating on the outside to achieve a hard substrate and lubricity combination not found in a single process. All of these coatings would require a lubrication engineered to support higher volume. One final word of caution on coatings. If your tube material is typically dirty, having a lot of debris and grit, then that will eventually lead to premature wear and failure of the coated mandrel. Since the cost is significantly more than a normal mandrel due to the specialized steel and coating process, this is something to consider if that can be managed to protect your investment. For softer tube like copper and aluminum, Delrin nylon plastic can offer a non-marking solution for the inside of the tube. Obviously, with the plastic having a much lower durometer than any metal, the life of these parts will be significantly less. Due to the lower life, we often see these deployed in an inserted nose configuration to avoid the expense of frequent shank replacement. An alternative aluminum bronze to the ones that Jack mentioned before is an AB21 or an equivalent ANSI grade. This material is a much harder alloy than normal aluminum bronze. However, it is also far more brittle and prone to breakage failures. We occasionally see this material used in specific aerospace applications, but normally it does not do very well in thin wall and ultra thin wall balls due to the lack of toughness. Ideal use would be for shanks and noses in high volume applications where there isn't a high impact potential, either from excessive tube collapse or machine crash. Another alternative to a traditional mandrel is cable mandrels. Cable mandrels are options for repetitive, easier applications. The design of the cable mandrel allows for full nesting of the balls within one another, which leads to little or no gap between the ball, and sometimes more support for the inside of the tube. The downside is the nesting results in increased wear on the balls, and there are issues bending tight bends due to the strength of the cables. Cables are also expensive and need replacement often as they stretch out over time. Another alternative to traditional mandrels would be chain link mandrels. These are typically used for square, rectangular, and shaped mandrels due to strength advantages. Chain links can be used for round mandrels for specific applications where more link strength is required but cost significantly more than traditional links, and require the machine to be modified to ensure that the mandrel stays aligned to the bend plane and does not rotate like a normal mandrel. These links are stronger than normal round links due to the single plane of bend. You can reassemble these links, but it is much more complicated than normal links. Mandrelless tooling is an option for smaller tubes on larger bends that don't have high quality standards. You will sometimes hear these tools referred to as heart-shaped or pinched bending, because the tube groove in the bend die and the pressure die is elliptical instead of round. This allows the tube to form an arch which supports itself through the bending process. This cannot be used in any application where a wiper is required, which means the bends typically have to be 2.5D or higher, and the wall needs to be fairly thick relative to the tube OD. Long term, eliminating the cost of mandrels can result in savings. However, the initial tools are much more expensive due to the increased machining and material required to support the impacts. The tube is also comes out of the bend with visible defects and isn't suitable for normal aesthetic products. For square, rectangular, and shaped tubes, one option is crush bending. This option is similar to mandrelless tooling in that it impacts the tube shape to eliminate the need for mandrels. The crush effectively allows the neutral axis to move towards the outside radius, resulting in less collapse. The defect is generally repeatable, but the distortion is pretty significant on the outside of the bend. Cost is similar to mandrelless tooling. Finally, if you can push your radius larger and use a larger wall, you can eventually get to a point where no mandrel is necessary to make a decent looking bend. You still may get a little more collapse than normal, but generally the rotary draw process has enough containment of the bend to prevent ugly defects like wrinkling, collapse, or kinking. At around 4D of bend, for example, a 2-inch OD on an 8-inch CLR, in order to avoid a mandrel, you would need about a 15 wall factor, which would be about a 1/8 inch or 0.125 thou wall, 125 thou wall. For 5D of bend, or 10-inch CLR on the same 2-inch OD, you can avoid a mandrel with a 25 wall factor, which would actually allow for an 80 thousandths wall on a 2-inch OD too. The selection chart that Jack reviewed earlier should be able to show you how to avoid a mandrel with no special features or tooling. One thing to consider when you increase the radius is that the final bend radius after the bend might not be what the tooling was cut to. Above a 4D bend, the impact of angular springback, where the final bend angle relieves once the clamp is released, and radial growth, where the radius also releases in similar fashion, can impact the final bend radius anywhere from upwards of 5% depending on the application. This may require a recut of the bend die and other tools if your radius tolerances are tight. That's a quick overview of the alternatives to traditional mandrel bending. And with that, the final end of our presentation. We will be answering questions on the phone number that was provided earlier. The phone number is 720-650-5050. Again, that's 720-650-5050. And the meeting ID that you will connect to is 415-703-537#. Again, the meeting ID is 415-703-537#. We will also include this information in the chat box on this presentation for you to dial in and answer questions. Thank you again for your time. And with that, we will transition over to the call and have our Q&A session.